everyone, this is Dr. Sirisha working as Associate Professor in Institute of Aeronautical Engineering College. Today we are going to learn about asymptotic notations. What is this notation? Generally, it is a mathematical term which we are going to learn about, and it has three types of notations and where we use it. Let's go into that. Let's talk about performance analysis. What performance analysis is basically? Analyzing any algorithm is nothing but performance analysis. Say, for example, I have 1,000 pages and each page takes 10 seconds to analyze. To get that is, maybe it may be the system may be using a compiler or an interpreter, whatever it may be. It is taking 10 seconds per page. Or you can take an example of an image editor, which is taking 1 hour to rotate your image to just 90 degrees. So such a huge amount of time they are taking. I'll just say that the compiler or interpreter or the image editor, whatever you are using, they are trash. It's waste to work with them. You'll end up into a dead loop if you work with huge image or more number of pages. So they are the worst ones to work with. So it is in simple numericals. I have explained you how we are going to analyze the performance. See how much time the compiler or interpreter is taking, right? Similarly, the performance we can analyze based upon the friendliness. You can clearly see that here the two systems are not at all user friendly. Okay, so the friendliness and the modularity we need to keep in our mind. The security which it provides, maintainability, sustainability, flexibility, loads of factors are there, my dears, which we need to consider when we go for performance analysis of an algorithm. How we analyze the performance of two algorithms. Two algorithms are there. A problem is there for that. Two algorithms have been designed. Which one works best? You need to understand that. Have to analyze it. So better take same input, run on the same system, see how much amount of time algorithm A takes and algorithm B takes. Or it also depends upon what kind of system you're working on. So for the same input, take two different systems and place these two different algorithms and try to work on it. So in this way, we can see that the first algorithm on the first system is working better than the second algorithm on the second system. And if you change the input, the story may get reversed. Just if you change the input, the story may get reversed. So there are a number of factors which we need to consider. So I can clearly say that whatever the parameters that influence the performance of an algorithm is nothing but the scale of that algorithm. So simply I can say that performance is nothing but the scale or the scale on which I am going to evaluate whether the algorithm is working better or not. And coming to the analysis, performance analysis, I can do using asymptotic analysis. It is a very huge idea which handles or operates on the issues in analyzing the algorithms. Okay, let's go deep into that. Let's put a deeper insight. Right. Coming to the asymptotic analysis. Asymptotic analysis, what it says. We generally think that the performance of an algorithm is totally upon the time and space it takes. Very good. But if you think deeply, the time and the space used by any algorithm varies with the size of input you take. That means directly or indirectly, the size of input which we take influences the analysis, which is nothing but asymptotic analysis. Let me take an example of searching techniques to explain you the same. I've taken linear search and binary search, where linear search is whose complexity is linear in nature, whereas a binary search complexity is in terms of logarithmic, right? So LS I'm using for linear search and BS for binary search. Let's work with these two. I have fed linear search algorithm into a fast computer A and binary search into a slow computer B. So the amount of time taken by linear search is zero point 0.2, whereas binary search is 1000 units of time. As a whole, I can clearly say that A is 5000, and that is linear search is going to give me a result 5000 times faster than B, right? Faster than B. But you clearly know that linear search works in a linear fashion, whereas binary search works in a logarithmic way, right? So let me generalize this one. For n number of inputs, the linear search is going to take zero point 0.2 into n, whereas binary search is going to take 1000 into n, which is a very high amount. So let's analyze the same. What will happen if I change the value of n when I start working with my algorithms LS and BS? Let me erase this one first of all and let us analyze the things, right? So let me analyze this one. Say the value of n, what n value and how LS performs and BS performs. Indirectly, I'm evaluating the system A and the system B, whereas system A is a faster system and B is a lighter, that is slower system. Okay, if my data size, the number of inputs which I take, if the value of n is 10, then A will take just 2 seconds, whereas binary search will take approximately 1 hour. If I increase the size, say 100 value of n is 100, and n number of that number of test cases is 100, then linear search will take 20 seconds, whereas this will take approximately 1.8 hours. If I increase the value of n exponentially, say 10 power 6, that is 10 for 1 followed by 6 zeros, 10 power 6, then my linear search will give me an approximate 55.5 hours. Yes, you have seen it absolutely right, my dears. Linear search will give me a result in 55.5 hours, whereas binary search will give me the result in just 5.5 hours. What if I increase the same? Increase the value of n further. 10 power, say 9 if I take, then this will take nearly 1 year to give me the result, and this will take around 8.3 hours. Have a look how it changes. The value. You can clearly see that whether you are working with a slower system or a faster system is a different story. Altogether a different story. But the complexity purely depends upon the size of input which you give. The size of input which you give. You have seen that if n value is just 10, then a linear search gave in 2 seconds the result, whereas binary search took roughly 1 hour of time. Right? So it's such a huge amount of time it is with a binary search, even though its complexity is logarithmic. As you keep on raising the value of n exponentially, then you can see a drastic change, right? So the graph has gone tipsy-turvy. So you can see that clearly. It is not a matter of faster computer or a slower computer. It is all dependent upon the value of n which you are going to use. Okay, so with this note, I can say that the complexity, and one more, genuinely, I can say that asymptotic analysis is not so perfect one. I'll tell you why. Once, how we analyze an algorithm. Please keep this in mind, and then I'll come back to that point. Why I'm saying that asymptotic notations are not so perfect. Have a look at this one. So any algorithm can be analyzed based upon three cases: the worst case, the average case, and the best case. So, let's take an example of, say, linear search. So, the worst case will be, what if you are trying to search for an element which is not present in the list itself? So, that itself is the worst case. So, WC is the worst case, and the complexity of that will be theta of n, where n is the number of elements in my list. The list where I'm searching for my key value, right? Worst case, where the element is not found itself. Second one is my average case. Average case, generally how we do it is by taking all the cases, considering all the cases, all possible cases, some the time which you have taken for all the individual cases, divide by the total number of cases. Means, what if in this linear search, if I'm using linear search, what if when I'm trying to search for an element is the first element itself? That is one case, how much amount of time you took. Then the second is how much amount of time you took to search the second element. If the element is the second one, what if it is third one? What if it is n minus 1th one? What if it is nth element? What if the element is not found in the list itself? Right? So all these are the cases which we cover when you try to search for an element using linear search. So in an average case, we have to sum the times which are taken by all these cases by the total number of cases. Then you are going to get the average. So the prerequisite for this one is a mathematical distribution that you need to know. The mathematical distribution of all the possible inputs. So for linear search, I can take it as summation of I is equal to 1 to n plus 1 theta of I by n plus 1. Why n plus 1? We have n elements, ma'am. Why you have taken n plus 1? I have taken n plus 1 because there is a case where the element is not found. The element is not present in the list. Even I have to consider that case also. So I have taken n plus 1. Then what is the result of this one? So sum of first n natural numbers. I hope you know the formula. N into n plus 1 by 2. So this will be n plus 2 by 2 by n plus 1. Okay. So this is nothing but theta of, right? Which is equal to theta of n. The complexity is the same, right? So theta of n. Then comes my best case. What will be the best case? What if the first element itself is the element which you are searching for? Then you are going to simply run for only one, so the theta is 1. Right? So these are the three types of cases based upon which we analyze an algorithm. It can be the worst case, average case, and best case. Sincerely saying, guys, never ever evaluate an algorithm based upon the best case. Never expect that. What do you think? In thousands of test cases, it will be rarely you'll find one or two cases where you are trying to find an element which is the first element in your list. And even the average worst case, even the worst case scenarios will also be rare in nature. You are trying to search for an element which is not present in the list. Coming to average case, it's very complex when the list size increases. Even we learn that why we migrated to binary search when we know how easy linear search is. Why we migrated? Because its complexity is very high. If you are working with handful of elements, just compare the elements, it's fun to do that. But if you have a huge set of elements, thousands of elements are there in your hands, comparing the k value with each and every element is a very tedious task, right? So even the average case time complexity is very high to on an average. Okay, so on an average, all the three are nearly average case is the best one. My opinion, average case is the best one, but its time complexity is high, and it whatever the case you take, even in a binary search, any sorting algorithm, bubble, insertion, selection, any algorithm you take, whatever algorithm you take, insertions in a trees or graphs, something like that, anything you take, average case time complexity raises, because you have to evaluate for each and every possible situation, right? So even its time complexity is high, it gives you a better result, right? So yes, let's come back to the analysis, that is asymptotic analysis of our algorithms. So when we work with the worst, average, and best case, asymptotic notation, the asymptotic analysis goes with the uh, calculations, right? And these calculations, say for example, if you are working with an algorithm and its complexity is say 5n square, and this for the first algorithm, and theta 2 is 1000n square, then the theta 1 will be order of n square, even theta 2 will be order of n square. There is no change in it, right? Both are one and the same. So because the constants do not influence, the complexity, or do not raise the complexity of any algorithm, right? We know that. So the mere constants 5 and 1000 do not fit you anything. Okay, so asymptotic analysis is not so good analysis also, right? So let's go a deep inside. So the main idea of asymptotic analysis is to measure the efficiency based upon the input which we give. So it is not dependent on machines or their configurations or constants. It is not dependent. So a mathematical notation of the same is nothing but your asymptotic notations. There are three types of asymptotic notations. One is theta, the other is big O, and the third is omega notation. Okay, so let's go and understand a deep insight what are these three notations and how they work. Okay, let's start with theta notation first. Theta notation is the most prominently used one when compared to big O and omega. Why? Because it considers the above and below limits of a given function. So as you know, it goes with the extreme boundaries of a given function. So it defines the exact asymptotic behavior. So how an algorithm behaves when it is fed with a lower boundary value, and how it behaves when it is given with a highest extreme value, and all the intermediate cases. It considers both, right? So it is the most prominently used one, theta. And the functionality of this function in this theta is, for example, for the given graph, consider the given graph where the graph is drawn for a function. We are trying to evaluate a function g of n with theta, and it works on a function f of n. It is a factor of f of n. Then there exist three positive values, c1, c2, and n0, such that the gn, the functionality of g of n, is between c1 and c2. You can see that it lies between 0 to the constant value g2 into g of n, or you can precisely, if you talk in terms of the resultant function f of n, it will be between c1 into g of n, where it is the lower limit, and c2 g of n, where it is the upper limit. So the resultant values of f of n lies between the lower and upper boundaries of the given function g of n, the input function basically g of n. So such a notation is theta notation. Okay, let's go for the next one, big O notation. Big O notation works with the upper boundaries. The upper boundaries. For example, say, let's take the example of insertion sort. Okay, so its best case is insertion sort, the best case is linear in nature, whereas its worst case is quadratic in nature. I'll tell you what the best case is. So for insertion sort, the best case will be a case where the list is already sorted. If you want the list to be in ascending order, and in your hands you're already having an ascending order list to get sorted, that itself is the best case, and its order is linear in nature. For the same insertion sort, the worst case will be, can you imagine, guys, if the list is reverse in order? That means in your hands you have a descending order list, and you're supposed to convert it to an ascending order. That is the worst case in case of insertion sort. Worst case in case of insertion sort. Okay, so the algorithm is the same algorithm, but you can clearly see that the best and worst cases influences the working of that algorithm. They analyze or they evaluate the performance of that algorithm. So that can be done easily with your big O of notation. Big O notation. Why? Because the best case, that is already you have the list in your required format, and what then you need not do much work. That is the complexity is linear. Then why to consider that case? There is no point in considering that case, right? So just straight away go for the worst case. That is upper boundary. Big O notation does it. It does not consider the best case. It considers only the worst case. Right? So I'll give you one more example, guys. Merge sort. I hope you know that. Its complexity in best, average, and worst. All the three cases is n log n. It doesn't change. So for merge sort, going with the big O notation is best, because here we are considering only the big O notation. We use only the upper boundary. We do not consider the lower boundary, right? So in merge sort, it is not biased whether the list is already sorted one, unsorted, or reverse order, whatever that is. Best, average, worst case, whatever the three cases it may be, merge sort works in a uniform way. It treats every case in a similar way. So its complexity, for to evaluate its performance and complexity, we use theta notation rather than big O notation, because it treats everything in a uniform way, right? Coming to insertion sort, you can see that its best case is is giving very less complexity. Then what is the fun of evaluating? Do you really feel that all the time you will be given a sorted list to sort? No one will give you, right? So it's ways to consider the best case, go for the worst case. That's why we go for the upper boundary, right? We go for the upper boundary. So in this case, that is for insertion sort, big O notation will be the best one, whereas for merge sort, theta notation will be the best one. Try to understand the hairline difference between these notations, my dear. All the three are mathematical notations, but all three notations are not good for all the cases. They are not universal. right? So depending upon the case, we go for the notation which is most relevant to that. Most relevant to that. Okay, come back to our bigger notation, guys. So to evaluate the function g of n, so the function there exists a positive value c, a constant value, a positive constant c and n naught, such that the function f of n values it lies between 0 and the constant multiplied by g of n. That means it lies between 0 to c into g of n. So these are the limits of a big O notation. So big O notation takes care of only the upper boundary. It is least bothered about the lower boundary. Okay, so insertion sort is the best example for the same. Okay, let me give one more example to you. Merge sort, all the three cases are theta of n log n. What about quick sort? Any idea about this one? When can you say that quick sort works best? The best case of quick sort is a case where the pivot element divides the list into two equal halves at each and every iteration. So remember this one, guys. These points are very important for your competitive exams. The best case scenario for quicksort is when the pivot element, that pivot element can be the zeroth indexed one or the highest indexed one, a middle value or a random value, whatever it can be. Okay. So if the pivot value divides the list into two equal halves at each iteration, then we call that to be the best case of quicksort. Okay, right. So this is a note on big O notation. Let's go with the last one, which is omega notation. So omega notation is a contrary to big O. Big O deals with the upper, whereas omega deals with the lower. So I'll give you a simple example. If there is a case where you have $1 million in your pocket and you throw a statement saying that I have an amount of money in my pocket and it is at least $10. At least $10. You have $1 million in your pocket, but you're claiming that I have at least $10 in my pocket. That means you're talking about the lower boundary, right? So such a rotation is omega notation. Any problem where you take the priority of the best case, in keeping the best case in your mind, if you work with, then omega notation. Essentially saying, we rarely use omega notations because whenever in real-time systems, in previously also I was talking about fast systems working on linear set, slow system working on binary sets. Coming to reality, go for a reality check, guys. I said that if you work with a data of 10 per 9, the size of n, when you work with linear sets, you will take 1 year approximately. And if you work with a binary set, it will just give you in roughly 8 hours. Right? So do you think you are going to work with a data set of 10 per 9 in reality? If you go into reality, I don't think in general applications we deal with such a huge data, right? So it all depends upon the total amount of time, right? So total amount of time taken, right? By a time taken by the sample case, input sample case. And go practical with the sample sizes, guys. That is the only point. So we have seen the three basic asymptotic notations. Asymptotic notation is nothing but mathematical tool to analyze asymptotic notations, that is asymptotic analysis. Representing asymptotic analysis in mathematical form is nothing but asymptotic notation. We generally go for big O or theta. Rarely we use omega because omega deals with lower boundary. Okay, so let's go with a few properties of the same. So the few properties of asymptotic notations. So the general property, the first and basic general property is, so if f of n is big O of g of n, then a into f of n is also big O of g of n. Very simple, guys. I'll give you a small example. If f of n is equal to n square, then big O of f of n will be n square. No change in that. What if I change this function or multiply this function with 7, right? So it will be 7n square. Even for that, that f of n will be n square only. It is not going to change, right? So 7 is a constant which do not affect the complexity, right? So, and the same property works for our theta and omega notations also. Okay, right. Coming to the second property, transitive property. So, if f of n is order of g of n and g of n is order of h of n, and then f of n is order of h of n, there is a relation, right? So, let me take an example, a small example. Say f of n is equal to n, g of n is equal to n square, h of n is equal to n cube. A simple example. Okay, so order of say f of n is order of g of n. Yes, it is order of g of n. N is n square. Order of n square is n cube. Then n is n cube. Very simple. It is transitive, right? So with this, I can say that theta, so big O notation is transitive in nature, right? So and the same works with your theta and omega, which I have explained using transitive property. Coming to reflexive property. So if f of n is a given function, then f of n is big O of f of n. It is reflexive. The function, the maximum value of f of n will be f of n itself, the function. It will be itself, right? So let me take an example and explain you the same. For example, f of n is equal to n square and its order of n square, that is f of n. Or let me write. One sec, let me write it more clearly. So big O of f of n is equal to order of n square. It's as simple as that. Reflexive, right? What is big O of f of n? Where f of n is n square. It is this one. Or I can take n square plus 5n. Even in that case also this works well. So n square plus 5n. What do you think? Big O of n square plus 5n. It is n square, right? So reflexive. And this same property works for omega as well as theta notations also. Okay. So next comes is symmetric property. Let me give you an example for that. So say f of n is equal to n square and g of n is also n square. Then we go of, so theta of f of n is equal to theta of g of n. Both is n square, right? So symmetric property satisfies only theta modules. Why? Because it deals with the upper as well as lower boundary. We cannot simply say that it is going to work for big O and omega notations also. Symmetric property is satisfied only by theta notation, but not by the remaining ones. Okay, then the last one. The last one is transitive symmetric property, which satisfies only for big O and omega notations, and it doesn't work for theta notation. So symmetric property works for theta and transsymmetric property works for the remaining two, omega and bigo, because they deal with only one boundary, not the both, right? So an example for that is, what if f of n is say n and g of n is n square, right? So order of f of n is n, whereas order of g of n is n square, right? So lower bound goes with the lower bound and higher bound goes with the higher bound. So this is the transpose symmetric property which works for only bigo and omega notations only. Okay, it doesn't work for theta notation. Okay, so these are the few properties of asymptotic notations. In this note, I would like to conclude that asymptotic notations are nothing but mathematical tools required to represent or required to represent the asymptotic notations. Okay, asymptotic analysis, which is nothing but performance analysis of algorithms. The whole story is revolving around analyzing algorithms. So every problem may have n number of solutions, right? But which one is more appropriate to use? By evaluating its performance only we can do that. And this evaluation we are going to do by in an asymptotic way, and for that we are going to take the asymptotic notations, that is mathematical tools help to evaluate the same, which goes with these properties, and the three notations are bigo, theta and omega. Okay, with this note I'd like to say that it is a brief note on asymptotic notations. Guys, please do follow my channel, and thank you for listening me so patiently. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.